Hello students, in this video we will solve some problems based on topic Hooke's law and pressure in fluid. Here draw a graph of extension against load for a spring which obeys Hooke's law. So this is a graph between extension and load, and x is the limit of proportionality. Up to x the graph will be straight line if it follows Hooke's law. State the word used to describe the energy stored in a spring that has been stretched or compressed. So it is elastic potential energy. Now in this figure, a train is traveling at a speed v approaching a buffer. The train mass is giving it is 2.5 kilogram. It is stopped by compressing a spring in the buffer. After the train has stopped, the energy stored in the spring is 0.48 joule. So we have to calculate the initial speed v of the train. We know that train kinetic energy is equal to energy stored in a spring. So the formula for kinetic energy is 1 by 2 mv square. M is the mass, it is given 2.5 kg. V we have to calculate, and it is equal to 0.48 joule, the energy stored in the spring. So V is equal to 0.62 meter per second. Here an athlete of mass 64 kg is bouncing up and down on a trampoline. At one moment the athlete is stationary on the stretched surface of the trampoline. This figure shows the movement. State the form of energy stored due to the stretching of surface of the trampoline. So it is elastic potential energy. The stretched surface of the trampoline begins to contract. The athlete is pushed vertically upward and she accelerates. At time t, when her upwards velocity is 6 meters per second, she loses contact with the surface. Calculate her kinetic energy at time t. So the formula for calculating kinetic energy is half mv square. M is the mass, it is given 64 kg, and v is the velocity 6 meters per second. It is 1152 joule. Joule is the unit of energy. Calculate the maximum possible distance she can travel upward after time t. So at maximum possible distance, the kinetic energy would be 0, and this will convert into maximum potential energy. Potential energy is mgh. So mgh is the gain in potential energy, and it will be equal to loss in kinetic energy. So it is 1152. So we can calculate h is 1.8 meter. In practice, she travels upwards through a slightly smaller distance than the distance calculated in second. Yes, due to the friction, there will be loss in the energy. So the h will be reduced. The maximum height will be reduced. The trampoline springs are tested. An extension load graph is plotted for one spring. And this figure is the graph. X is the limit of proportionality. State the name of the law that springs obey. It is a Hooke's law because the gradient is constant in this region. This figure shows a part of the extension load graph for a spring. This is spring obey Hooke's law between point A and B. On this figure, complete the graph between A and B. So it will be a straight line because it is following Hooke's law. The gradient of extension versus load graph is constant. State the name of the point B. B is limit of proportionality. The average value of the load between A and B is 6 Newton. So average value is 6 Newton means at A the load is 0. At B it is 12. Average value will be 0 plus 12 divided by 2. So it is 6 Newton. And at this load the extension is 3 centimeter means 0.03 meter. So work done is equal to force multiplied by distance, the extension. It is 0.18 joule. The spring has an unstretched length of 4 cm. An object is hung on the spring and the spring length increases from 4 cm to 6 cm. Calculate the mass of the object. So from the previous graph, we could calculate the value of k, and k is equal to f by x. So if you divide 12 by 3, f is the load and x is the extension. So the value of k spring constant is 4 Newton per centimeter. Now here the data is given that the length increased from 4 cm to 6 cm. So extension is 2 cm here. We have extension x and the value of k also. So load F is equal to 8 Newton. Now we know that F is equal to mg. So m is equal to force divided by g. It is 0.8 kilogram. In second part, the object is immersed in a liquid but remains suspended from the spring. So the liquid exerts an upward force on the object and the length of the spring decreases to 5 cm. Calculate the upward force exerted on the object by the liquid. So F is equal to now minus Kx. So K value we know it is 4 and X is 6 minus 5 because it is the contraction in the length of the spring. So it is minus 4 Newton. Minus sign shows that this is a restoring force on the spring. This figure shows a graph of the stretching force F acting on a spring against the extension of the spring X. F and X is the load and this is the extension. State the feature of the graph that shows that a spring obeys Hooke's law. As the gradient is constant, so a spring obeys Hooke's law. Calculate K, the force per unit extension of the spring. K is equal to F by X. F is 75 here. The value is 75 and X is 30. So it is 2.5 Newton per millimeter. Since the dimension, the unit of X is given, it is millimeter. The limit of proportionality of the spring is reached at an extension of 50 millimeter. Means 50 millimeter. This is the limit of proportionality and here the load is 125 Newton. So continue the graph here to suggest how the spring behaves when the stretching force is increased to a value above 125 Newton. So extension in the length of a spring will not be proportional to the applied force or spring does not obey Hooke's law if load is further increased to above 125 Newton. Now another spring has a smaller value of K. It means the K value is smaller than the earlier spring. The earlier value of K was 2.5 Newton per millimeter. This spring obeys Hooke's law. So it means that if we plot a graph between force, load and extension, since this spring obeys Hooke's law, it will be a straight line. The gradient of this spring also constant. Now this obeys Hooke's law up to 80 millimeter means up to 80 millimeter the line is straight. Since it has a smaller value of K, so the new line will be less steeper as compared to the previous line because greater the spring constant, steeper gradient of the graph line. A spring S is suspended from a clamp stand in a school laboratory. A student hangs various masses from the end of S and determines the extension X by each mass. The student plots a graph of the force F applied to the spring against the extension X. This figure is the student's graph. Calculate the weight of 250 gram mass. So weight is equal to mass into G. It is 2.5 Newton. The value of G is approximate value of G. It is 10 here. Use the section of the graph where the spring S obeys Hooke's law. So spring F obeys Hooke's law up to point P since P is a limit of proportionality to determine the spring constant K of the spring. Now K is equal to F by X. So we can choose any corresponding value of F versus X. We have taken 3.6 value and the corresponding value of this load is 8. So K is equal to F by X. It is 0.45 Newton per centimeter. This figure shows a mass of 0.12 kg resting on the bottom of a box. Now a spring that is identical to S connects the mass and one side of the box. Ignore friction between the mass and the box. The box and the mass are at rest. State the resulting force. So definitely the force is 0 since the mass is at rest. The box is firmly attached in a horizontal position to the body of a racing car. As the car accelerates, the spring stretches by 2 cm. So using the earlier figure, this one, we calculated the value of K here 0.45 Newton per centimeter. Determine the tension. So tension force is equal to Kx. K is 0.45 and X is 2 cm. It is 0.9 Newton. Calculate the acceleration of the mass. We know F is equal to ma. Force is equal to mass multiplied by acceleration. So it is force divided by mass. Mass is given 0.12 kg. Now acceleration is 7.5 meter per second square. An experiment is carried out to measure the extension of a rubber band for different loads. The results are shown here. Which figure is missing from the table? It is the length. It is the load. When there was a zero means no load, the original length of the spring, the unstretched length was 15.2 centimeter. Extension is 0. When 1 Newton load is hung, the length becomes 16.2 and extension is 1. 16.2 minus 15.2, it is 1. So similarly, extension is equal to total length minus original length. Now extension is here 2.1. Total length x, let's consider x. This is the total length missing minus the original length. It is 15.2. Now x is equal to 17.3 centimeter. Objects with different masses are hung on a spring. The diagram shows how much the spring stretches. We know that F is proportional to extension and F is equal to m into g. M mass multiplied by g. So what is the mass of object m here? Here, since there is no load, it means 10 centimeter is the unstretched length or the original length of the spring. Here, when the mass is 100 gram is hung at other end, the total length of the spring becomes 20 centimeter. It means the extension is 20 minus 10 centimeter. In case 3, we have to calculate this mass m and the total length of the spring is 30 centimeter. It means the extension is 30 minus 10, 20 centimeter. Is equal to kx and k is a constant which is f by x. So f1 upon x1 is equal to f2 upon x2. 100g divided by extension 10 centimeter, 20 minus 10 is equal to mass into g, because we know f is equal to mg divided by 20. So mass m is equal to 200 gram. Option C is right here. The diagrams show a steel spring and a graph of its length against the load applied to it. What is the extension of the spring when a load of 20 Newton is applied to it? Here, when load is 20 Newton, the length is 8 centimeter. And when there was no load, the original unstretched length was 5 centimeter. So extension x will be 8 minus 5, 3 centimeter. Because extension is final length minus unstretched length when load is 0. Two metal blocks P and Q have identical dimensions and they hang on identical spring. It means K spring constant is same and volume is same because they have identical dimensions. What can be deduced about P and Q? They have different volumes? No. They have same volumes, identical volumes. They have different? No. They have equal volumes and equal weights. Weights are different because extensions are different. Since K value is same, extension is different. They have equal volumes but different masses. Yes, this is the right one. They have equal volumes and their weights are different. Since G is same, so it is the mass which is responsible for different weight. The extension load graph for a spring is shown. The unstretched length of the spring is 17. Unstretched length definitely when the load is 0. And when an object is hung from the spring, the length of the spring means total length of the spring becomes 19.2 centimeter. So extension x is equal to 2.2 centimeter. Now 19.2 minus 17, 2.2 centimeter is the extension and the corresponding value of load when the extension is 2.2 centimeter is the 3 Newton. So answer is 3 Newton. Thank you. Thank you very much for watching this video. Please like, subscribe and share and don't forget to leave your comment here. Thank you once again.